This will be an introduction to ligand exchange in inorganic complexes, and we're going to use octahedral complexes as our main example here. So we're going to review the main mechanisms of exchange and think about the connections that there are between what you've learned before in organic chemistry compared to inorganic reactions. So for the example today, we're going to consider a metal complex with 6 ligands. We're going to name 5 of those ligands L, and we're just going to not worry about what those are for most of the part. And the other ligand will be some leaving ligand X. Okay, so this X here will be the ligand that is exchanged. And an incoming ligand will be named Y. Okay, so in some way we're going to have a reaction between this complex and the incoming ligand. So the exchange reaction will look like this. We're going to have our initial complex Ml5X reacting with Y and exchanging. So Y is going to replace the X, and we're going to have a product Ml5Y. Okay. So the question is, how does this occur? It doesn't just pop on while the other one pops off. There must be a mechanism that causes this to happen, and that's what we're going to explore. So the first mechanism we're going to examine is called the associative mechanism. And in this case, we have our same complex with our leaving ligand and 5 other ligands. I'm not going to label them here. And it's being replaced by Y, as we saw before. But in this case, we have a transition state, Ml5XY. And so in this transition state, both X and Y are somehow associated with the metal complex. That's why it's called associative. So this is not an intermediate. This is a transition state because you see there's no way to trap that complex. And so it's just an activated complex. That's what that little star means. If we think about the kinetics of this reaction, the rate is limited by the activation barrier, the energy, which is described by this activated energy here, delta G star. And so this determines the rate constant, is the height of this slope right here. Okay. And so when it's done, Y stays, X will leave, right? And so this is the process, Y coming in and X leaving, but in between we have a complex which has both of these associated at the same time. And so the question is, how is this connected to what you learned before? So what organic reaction had, in that case, a carbon, some carbon with some outgoing leaving group and some incoming nucleophile, right? And 3 other species all present at the same time. What was that mechanism? Well, that was the SN2 mechanism. Okay, the SN2 mechanism had the nucleophile bound at the same time as the leaving group was leaving. Okay, it had a transition state in the same way that this does. So the opposite of the associative mechanism is, not surprisingly, the dissociative mechanism. So in this case, we again had our same complex with our leaving ligand X and our incoming ligand Y coming in, right? But before Y associates, what we see is we have now an intermediate Ml5, which means that the first thing that happened was X popped off, right? So we have temporarily a complex that looks like this. It would certainly rearrange its shape if it has time, but this is our intermediate. And at that point, we have 5 ligands, and then Y can associate and bind to that complex, right? So in between, we have 2 different transition states. We have a transition state where X has partially left, right? And we have a case where Y has partially popped on, and both of those are less stable than either species on the sides of them. So this thing where X is halfway off is actually worse than having it all the way off. And so again, you look for the highest point, the highest energy in this diagram, which is typically that first dissociative step. And that determines your activation energy again. So the height of that barrier going from your Ml5X to this activated complex on the way to the transition state is the rate determining step. And that is dissociation, right? We've lost our ligand. So the question is, what does this look like in terms of organic chemistry? So where did you see something where the leaving group first leaves, and we form usually a cation here with 3 species? Well, that would be an SN1 mechanism. Okay, that's the one where you dissociate the leaving group first. And if you review back to those times, you find you learned a lot about what causes an SN1 versus an SN2 mechanism. And a lot of those same rules apply here as well. So unfortunately, it's never so simple as there are strictly associative or dissociative reactions. And in fact, that's generally not the case. It lies somewhere in between. And so that's called interchange. And so you could just say that most reactions are interchange reactions of some sort. Some of them are mostly associative and mostly dissociative. And so those are called interchange A and interchange D reactions. It's just saying that they're tilted towards one of those two main mechanisms. And so maybe it's best to think of these mechanisms as being a continuum between the associative side and the dissociative side, where interchange lies in that continuum. And so, again, a dissociative mechanism would be just the complete release of an outgoing ligand before the first one comes in, and then the associative mechanism is that transition state, the transition state in between, where you have both the incoming and outgoing ligand at exactly the same time. But it's likely to be the case where you have something where the bonds are beginning to form between Y and X, but maybe X leaves before Y is fully attached, right? That would be more dissociative. Or maybe Y attaches quite a lot before X begins to leave. That would be mostly associative, right? That's the interchange. So there are implications of these mechanisms, and we'll just think about the difference between these sort of two ends of the continuum and just understand that the interchange mechanism is some blend of those. But one of those is what effect does the incoming ligand have, right? So the only mechanism that depends on that incoming ligand is the associative mechanism, because in a dissociation, the first thing that happens is your leaving group leaves, right? Your leaving ligand leaves, and the incoming ligand hasn't gotten involved yet. So dissociative mechanisms are independent of the incoming ligand, meaning the rate constant shouldn't change if you look at different reactions with the same reactant, the same metal complex reactant, and different incoming ligands. The rate constants should be the same. And you'll find that in a close to dissociative mechanism, right, that it's like that. You'll see that the rate constants don't change very much. We'll look at data soon. And if it is associative, then the opposite is true. Then all of the rate constants are quite different depending on that incoming ligand. What about outgoing ligands? So this is a little trickier because both of the mechanisms have to eventually release that outgoing ligand. But of course, the dissociative mechanism, this is all that matters. So associative mechanisms are less affected by the outgoing ligand because what's really happening is you're forming that complex with all of them attached at once, right? But we'll see, especially in square planar complexes, that the effect of that leaving ligand is pretty strong. You'll see that there is the bonding between that ligand and the metal does change the way that the incoming ligand bonds as well. So it's not completely independent, it's just less dependent. And then there is an effect of other ligands in the complex, those L's we've been drawing, right? So this is pretty closely connected to a topic you would have talked about when you talked about SN1 reactions, right? So SN1 reactions are favored when this complex is sterically hindered, and this is the case as well. So if you have crowding or steric hindrance in your complex, then that makes it difficult for a new ligand to come in, and it also crowds out effectively that other ligand and makes it pop off more readily, depending on what kind of steric hindrance we're talking about. So it can speed dissociative reactions and slow associative reactions. So in the next set of notes, we're going to look at some data that gives some examples of this. We'll be able to see kind of relative rates of reaction and try to understand what causes this to happen. So before we go on, we need to identify some vocabulary for kinetics, and this is very easily confused, and I will probably mix it up sometimes when I'm talking inadvertently. But first of all, we tend to be sloppy with our use of these words stable and unstable. Okay, so stable means, it really means thermodynamically stable. Stable means that it will not fall apart, which means it's at the bottom of its thermodynamic well, right? Unstable means in some way, if you let it go in the environment that it's in, it will change. It will uh, exchange with ligands, or perhaps break its bonds and rearrange, so-called decompose. Something will happen to it, right? That's what unstable really means. So equilibrium causes stable products to form. The kinetic terms are inert and labile, okay? So inert means it will not change very fast. It doesn't mean that it's stable, okay? Labile means it will change very fast under its current conditions, and this must mean that it's also unstable, because if it was stable, it wouldn't be exchanging too fast. But sometimes you have a perfectly fine complex that's exchanging with its environment, say water exchanging other water molecules. This happens quite often, with quite rapidly with some complexes. So it's possible for this unstable complexes to be kinetically trapped if that complex is also inert. That means that even though there's a better ligand that could exchange for one of its ligands that's on there now, right? It's not going to exchange because the reaction is too slow. It can be, many years before that exchange begins to occur at an appreciable rate. One complex where that's the case is cobalt 3+. Okay, cobalt 3 is that typically low spin D6 complex, and it's classically inert. This was the first metal to be used as a framework to test ligand environments, and the laboratory you just completed is an example of that. So it's very possible to make lots of different, maybe stable, maybe unstable, doesn't matter, but kinetically inert complexes of cobalt 3.